Hi, I'm Ali Muzaffari and I have my other team members Muhammad Siddiq, Muhammad Qasimi and Hasnain Ali with me, and we are doing a spaghetti bridge assignment part 2.2 PowerPoint presentation. This this presentation summarizes our spaghetti bridge project. The aims was to design, construct, analysis and test a small-scale spaghetti truss bridge until failure. Our goal was to create a bridge that could support a high load while keeping the structure as light as possible. The bridge was inspired by a Howe truss design because it is a simple, strong, and uses triangular geometry to transfer load efficiently. Slide T. Our bridge was inspired by a Howe truss arrangements. We chose this design because it was simple to build, but still strong due to use of triangular members. The final bridge length was 360 millimeters, and width was exactly 80 millimeters, and the height was 87 millimeters. The bridge mass was 238 grams. This became an important point in our evaluation because the project limit was 200 grams, meaning our bridge was heavier than required. Although the extra material may have helped the bridge carry load, it reduced the overall efficiency. The main structural concept behind the bridge is truss section, a truss transfer load through connected members, mainly through axial tension and compression. In general, the top members are expected to experience compression, while the bottom members are expected to experience tension. The diagonal and vertical members help transfer the load from the center of the bridge towards the supports. Since spaghetti is brittle and weaker in compression, shorter compression, members are good joint connections are important for preventing buckling and sudden failure.
The construction process. The bridge was constructed using spaghetti and super glue. We first formed the side trusses frames and then connected two sides together to create the bridge width. The deck area was also included so the bridge could be transferred into the structure during testing. The most important construction challenging was keeping the bridge straight and making sure that the joints were bonded correctly. Because the spaghetti is brittle, small errors in member length, glue quality, or alignment can cause uneven load transfer and early failure. For testing, the bridge was placed on the testing machine and loaded gradually until failure. The bridge sat freely on supports, meaning that it was not anchored down. The load was applied to a testing setup until the bridge could no longer carry the force during the test. We recorded the video evidence so that the failure behavior could be reviewed afterwards. This is the video.
2, 3, 5, 10, 15,
Get it?
20, 20.
The bridge weighed 238 grams and carried a maximum load of 20 kilograms before failure. This is approximately 196 newtons. When the failure load is divided by the bridge mass, the load-to-weight ratio is about 84. This means the bridge carried around 84 times its own mass before breaking. The bridge width was exactly 80 millimeters, while the length was 360 millimeters, and the height was 87 millimeters. The failure did not occur at the center as expected. Instead, the bridge failed on the left side. The failure occurred on the left side rather than directly at the middle. This suggests that the bridge may not have distributed the load evenly through both side trusses. One likely reason is that the left side members are joints became the weakest part of the structure. Since the load was applied through the deck, force should have transferred through the truss members toward both supports. However, if one side had weaker glue joints, slightly uneven geometry, or less effective bracing, more stress may have concentrated on that side. The failure may also relate to compression behavior, because spaghetti members under compression can buckle or fracture suddenly. Overall, the failure showed that joint quality and symmetry are just as important as the overall truss design, as explained in this video.
20, 20,
The slot design worked well in the sense that it carried 20 kilograms before failure, which shows the truss arrangement was effective. The triangular form helped transfer load throughout the bridge, and the deck helped connect the loading point to the structure. However, the bridge was heavier than the required 200-gram limit, so the design was not as efficient as it could have been. A better version would reduce unnecessary material, improve the left side joints, and make the bridge more symmetrical, so the load is shared more evenly between both sides. In conclusion, the spaghetti bridge showed that structural performance depends on more than just adding extra material. The bridge carried 20 kilograms, but its 238-gram mass reduced its efficiency. The left side failure showed the importance of accurate construction, strong joints, effective bracing, and balanced load transfer. If we repeated the project, we would keep the Howie-inspired design, but reduce the mass, improve joint consistency, and strengthen the areas where the load transfers into the side trusses. This project helped connect truss theory with real structural behavior, especially tension, compression, buckling, loading path, and failure analysis.